my people. I hope we're doing well today. In the last section, we dealt with using trigonometric identities to change integrands, trigonometric integrands that were not integrable into ones that were. In this one, we're going to do something, I don't know, for lack of a better word, audacious. When we're presented with something like this, we notice that the main problem that we have with the fact that this is not integrable is the fact that we have a binomial in the radicand. Okay. Now, if this were trig, then oh my gosh, it would be so simple. We can use, Pythagorean identities to take something that is of binomial of two terms and change it into one term, and then we can actually execute that square root, right? But because of the order of operations and the fact that we can't sort of distribute a radical to each term, if it remains a binomial, it's unresolvable at present, right? So what we're going to do is we're going to use trigonometry to do that by substituting trigonometric expressions into a non-trigonometric integrand. So we're going to substitute those in, use the identities to change the form and to integrate, and then we're going to basically change it back into the original variable. Okay. Now, obviously there are three different Pythagorean identities. We've looked at those and we've reviewed those, and each one has three different forms. But basically, when you're left with these, there's really only two that you need to remember, and only two that we're going to use. I mean, you can use other ones, but it's not really wise to do so. If we have 4 minus a square, that kind of reminds us of 1 minus sine squared theta, right? Okay, so if we had 1 minus sine squared under here, or 1 minus cosine squared under here, we could basically change it into the other one. Now, of course, we have to deal with the 4. So what we're going to do is, instead of this x squared, I need it to be 4 sine squared theta. So x is going to be 2 sine theta. And if we substitute that in for the x right here, we're going to get something where we can then factor out the 4, and we'll be left with this expression, which can then be transformed using our Pythagorean identity into cosine squared. But of course, we have to substitute for all this other stuff as well. Now, dx is going to be 2 cosine theta d theta. And of course, x squared is just 4 sine squared theta. So whatever goes here also goes here. All right, let's go ahead and do that. So we have 2 cosine theta d theta, and that goes in for my dx. Okay, my x squared becomes 4 sine squared theta, and this underneath the radical becomes 4 minus 4 sine squared theta. Now, of course, I can factor out the 4, and so it becomes the square root of 4 times 1 minus sine squared underneath the radical. So let's go ahead and rewrite it like that. I'm going to skip very few steps on this first one just to make sure that we're all tracking. And so you have 4 times 1 minus sine squared. Now, that was the whole point of the trigonometric substitution. So that is going to become cosine squared. And the square root of 4 cosine squared is going to be 2 times cosine. So we wind up with 2 cosine theta d theta, 4 sine squared theta times 2 cosine theta. Well, that cancels with that, and what I'm left with is 1/4 cosecant squared theta d theta. Now, this integrand may not have been a recognizable It may not have been a recognizable derivative, but this is awfully close, right? All you have to do is turn it into negative cosecant x, cosecant squared that is, and of course we're going to get the integrand of that as cotangent. So we get negative 1/4 cotangent theta plus c. And we've actually taken trigonometry, introduced it, substituted it in for the x, used the trigonometric IDs and the trigonometric antiderivative rules that we know, and we have actually arrived at cotangent theta. Well, the question is, if x is equal to 2 sine theta, how do I get cotangent theta back into x? Well, remember that x is equal to 2 sine theta implies sine theta is equal to x over 2. Well, if sine theta is equal to that ratio, then we just need a little right triangle trig, and that tells me that the opposite over the hypotenuse of that particular angle theta is x over 2, leaving this side to be square root of 4 minus x squared. Now, from here, obviously cotangent is going to be adjacent over opposite, so when I substitute back in, I'm going to get the square root of 4 minus x squared over x plus c, or negative root 4 minus x squared all over 4x plus c. And, you know, if you were to go ahead and check it by taking the derivative of this, I think it's pretty easy to see by the quotient rule, you would wind up with that radical needing to be in the denominator to resolve the complex fraction, and of course this x being squared. Okay, I'm not going to go through it right now. I will actually go through it on some subsequent examples, but let's go ahead and move and get beyond this. Now, there are basically 3 ways that you're going to find these radicals or these expressions that require, or at least we can use, like some of them are required. If it's a radical, it's required. But there are actually examples where we can use trig sub, where actually other ones would work as well. Now on this one, we had the radical in the form of a squared minus x squared. Okay, that means we're needing to use the 1 minus sine squared. Okay, so whatever x is, we need to figure out a way for it to become, we basically need to figure out a way for it to become a squared minus a squared sine squared theta. Okay, so you need to figure out a way of what must x be to transform the x squared into this expression. Well, they're not always like that. Sometimes it's x squared plus a squared. At which point, you know, we're probably going to, we can use, you know, a couple of them, but what we're going to be using is the tangent squared theta plus 1, because that becomes secant squared theta. And so what you need is you need to substitute in for x such that we're going to get a squared tangent squared theta plus a squared, such that you can factor the a squared out and transform the binomial of tangent squared theta plus 1 into secant squared theta. And the last one, of course, is going to be x squared minus a squared. Because, of course, this one, it doesn't matter if you reverse the order, right? But these two are actually distinct. On this one, we're actually going to use the same trigonometric, the same Pythagorean identity. We're just going to use a different form of the tangent and secant one, and we're going to use the secant squared theta minus 1 such that the radicand can become a squared secant squared theta minus a squared. And of course, we're going to work through a ton of examples to show you kind of why that is and why it works. But that's the basic strategy of all of these. And so it's a little uncomfortable at first, but because there's really only 3 options, and you can tell from the form of that radicand what my substitution needs to be, it actually winds up, after a little bit of time and exposure, winds up being pretty straightforward. So We've already done one of the first variety, the a squared minus x squared. Let's move on to an x squared plus a squared. Okay, so I have the integral of the square root of 1 plus x squared. Now remember that 1 plus x squared, I'm going to be using 1 plus tangent squared so that it can become secant squared. Okay, well this one, it's really not all that difficult because a happens to be 1, and so I don't need to, x is equal to, some constant times tangent squared. It just winds up being x is equal to tangent squared. But remember that we also need to substitute in for dx, and dx is secant squared theta d theta. Okay, well let's go ahead and substitute in, and we're going to get 1 plus tangent squared theta times secant squared theta d theta, where we've substituted tangent in for x and this whole thing in for the dx. Now this is going to become the square root of secant squared, or just secant, and that combines with this secant squared and becomes secant cubed theta d theta. Now, from the last section, this was one of those special ones that we worked out on the videos. I don't know if you remember. And I'm not going to go through reworking it. I'm just going to remind you that it worked out to 1/2 times secant tangent plus the natural log of secant theta plus tangent theta plus c. Well, remember that this up here reminds us that tangent theta is equal to the ratio of x over 1. We can quickly, and from now on, basically when I do this, I'm going to go ahead and draw the triangle right afterwards. I didn't do that this time, so I'm going to have to pop down here to do it, so I didn't leave myself enough room. But if tangent theta is equal to x over 1, x over 1, opposite over adjacent, then the hypotenuse is, of course, 1 plus x squared. And when I substitute in here, remember secant is hypotenuse over adjacent, so you're going to get 1/2, and let's do the tangent first, x, and then the secant, 1 plus x squared, plus the natural log of x plus 1 plus x squared, all of that plus c. And that actually winds up being your integral. And if you want to go ahead and check it, you can. You would just have to basically set this as equal to 1/2 and then x 1 plus x squared to the 1/2 plus the natural log of x plus 1 plus x squared to the 1/2, and then basically differentiate. And when you do that, you would need to, of course, do the product rule here, and then, of course, u prime over u for the natural log over here. And when you actually clean it up, it does actually wind up being the square root of 1 plus x squared. And if you want to go ahead and try that on your own, feel free to do so. It winds up, it's just a lot of fractions and radicals embedded within the fractions and fun stuff like that. It's not actually all that difficult. It is, however, a little bit tedious and burdensome. But let's go ahead and move on to one of the third variety, where it's x squared minus a squared underneath the radical. Now that, of course, is still the tangent and secant identity, but it winds up being the different form. It winds up being secant squared theta minus 1 is equal to tangent squared theta. Now, could you use the cosecant and cotangent one? Sure. But why would you if you're more familiar with the secant and the tangent one, and you just kind of get used to doing it like this? This is kind of analogous to, can you anti-differentiate -1 over the square root of 1 minus x squared into arc cosine? Sure. But remember, why do so when the only difference between the derivative of arc sine and arc cosine is a negative? Why not limit the number of formulas you need to remember? So it's kind of that whole why be why be inefficient? Let's just go ahead and use this one right here. Now, my a squared, of course, is 16, so a is 4. What I need is, I need x is equal to 4 secant theta, which, you know, for when we do our triangle here in just a moment, that implies that secant theta is x over 4. Now, when I get the differential, this is going to be 4 secant theta tangent theta d theta. Okay, let's go ahead and make our triangle. Okay, we have theta, and if secant theta is x over 4, it's x over 4, right? It's hypotenuse over adjacent. And then this winds up being, surprise, surprise, x squared minus 16. Actually, that should surprise nobody. Okay, so let's go ahead and do the x squared, so that winds up being 16 secant squared theta. That's our x squared. Now let's do our dx. That winds up being 4 secant theta tangent theta d theta, all over the square root. And that square root is, of course, 16 secant squared theta minus 16. Now when I factor out the 16, that's going to become, underneath the radical, the product of 16 times secant squared minus 1. And that, of course, is going to be 16 tangent squared. So this denominator basically becomes 4 times tangent. Okay, so let's just simplify this up here just a little bit. Let's do 64 secant cubed theta tangent theta d theta. All of that over 4 tangent theta. Of course, the tangent thetas cross out. The 4 right here cancels with 4 that's inside the 16, and I'm actually left with 16 and secant cubed theta d theta. Now, after these videos, you're going to think, do they all wind up being secant cubed theta? Now, it turns out that a couple of the ones that I chose wound up being that, and it's just sort of a coincidence. But remember that it was 1/2 secant tangent plus natural log of secant plus tangent, and so the 16 times the 1/2 gives me my 8, and I'm left with secant tangent plus the natural log of secant theta plus tangent theta, all of that plus c. Okay, so basically, just like the last two, I saw this radicand, and I said, gosh, that's a binomial. I wish it wasn't. Well, I can't do that with polynomials, but gosh, I wish it was trig, because if it was trig, I could use Pythagorean identities in order to take a binomial down to a monomial. Oh, wait, let's go ahead and substitute trig in. So we basically artificially introduce trig into here and rewrite the whole thing in terms of what is basically an arbitrary equation. I use the Pythagorean identities to simplify, use my trigonometric integration understanding to get the integral, and now after I integrate, remember always after you integrate, I resubstitute back in. And this winds up being secant is obviously x over 4. The tangent is going to be opposite over adjacent, so it's going to be that radical over 4. And then plus natural log of x over 4 plus the radical over 4 plus c. Now, this up here becomes 1/16 times x times the square root of x squared minus 4, and this becomes natural log of x plus the square root of x squared minus 16 over 4. Now remember your properties of logarithms. This can be split up into 2 logarithms, and I'm going to do it explicitly this time. The next time I'm just going to get rid of the denominator. And the reason that I can get rid of that denominator is it just winds up being minus natural log 4. Well, when I distribute the 8, right, I'm going to get 1/2 x square root of x squared minus 4 plus 8 times the natural log of x plus that square root, and then this is minus 8 natural log 4 plus c. Well, c is already some arbitrary constant, so what happens when I combine c, arbitrary constant, with a real constant? It just becomes a different arbitrary constant, right? And so if you're dealing with the indefinite integral, you can actually clean it up a little bit by getting rid of that denominator within the natural log's argument and just turn it into plus c. Okay. Now, and again, if you were to actually take the derivative, this would all kind of work out nice and tidy. So I think that brings us to the end of our first video. That gives you one example of each of the 3 varieties. In the next video and succeeding videos after that, I'm going to pick up the pace a little bit and not march through so step by step. Just for the sake of getting through more examples, I'm going to skip the steps that you big bad Calculus 2 students should be able to do in your head and on the fly. But as always, if you have any questions, please do ask them, shoot me an email, and I'd be more than happy to address those when the time comes. Bye.